This is me. If you want to contact me, the numbers are on the right. Well, that's probably not going to be good. So when I first suggested, doing a talk here on Libbitcoin, is that sorry, how's that? Okay, it's good. One of the pieces of feedback I got initially was, well, Libbitcoin is Bitcoin. What are you building on Bitcoin? So Libbitcoin is actually more, which is what I'm going to talk about, but also going to talk a little bit about what it is underneath, because it really is an implementation of Bitcoin as well. I also, most of the talks I give are on crypto economics. I really don't talk about Libbitcoin very much. In my opinion, up until more recently, it hasn't been mature enough to go out and promote. I still feel that. I probably will always feel that way. So this is one of the first talks I've given on Libbitcoin, actually. So to me, it's important to cover some of the crypto economic principles behind what we're doing. Otherwise, what are we doing? We wouldn't really understand it. So building on Bitcoin, and it really is more than just building financial tools that use Bitcoin. It's really about building on Bitcoin, making Bitcoin not something that pulls people away from Bitcoin. So tools that increase individual power enhance it, and tools that reduce individual power diminish it. And what I'm talking about by individual power is what, say, you have in Bitcoin, how you help protect it. In other words, if everybody moves off to a centralized system for validation, for, say, mining, one person has say in everything. So what we want to do is build tools that build on Bitcoin, not tools that pull people away from Bitcoin. And this is, I have a slide coming up that'll talk a little bit more about that, but this is really what Libbitcoin is all about. Helping people build Bitcoin stuff, not encouraging people to use, say, a centralized API or service that really takes that power away from them. So that power is in terms of security is expressed by miners and merchants. Miners secure confirmation, and merchants secure the rules. They validate in a way that matters. So independent exercise of power implies you're doing it covertly. If you're doing all this very publicly, and somebody can step in and say, don't do that, and you're forced to comply, you really don't have the power. The person that has the ability to force you to comply has the power. So when we talk about decentralization and security in Bitcoin as a system, you have to ask yourself, why does decentralization matter? I mean, a lot of companies, corporations can be, like McDonald's is highly decentralized. Just McDonald's is everywhere, right? They're all over the place, but you can step in and enforce them to apply a tax law, right? Not a problem. So it's more than just decentralization. Decentralization exists so that people can hide. They have to operate at small scale. So it's really about anonymity. It's the essential security aspect of Bitcoin. And decentralization is just another way that people are allowed to be anonymous. If you're big, you can't hide. So Bitcoin relies on verifiable public data to achieve anonymity. There's no identity in the system. There's no permission required. Well, how does it achieve that? It doesn't achieve that through encrypted channels or nodes with identity the way banking systems work. It does that by giving everybody a copy of the same public data and allowing people to verify the data. So large operations are inconsistent with anonymity. Big corporate server farm that can be taken down. It's not anonymous even if there's no names attached to it, because it's visible, identifiable. So decentralization is important. So Bitcoin requires competitive performance for small operations. Sorry, hold on a second. Just give me a cup of water. I'm losing my voice already. So competitive performance for small operations. You have to be able to mine at a low level, small, and be competitive for Bitcoin to really work. If the only people who can do it are a couple large server farms, Bitcoin's not secure in any way. Or it's secure for the few people that do it, and as long as they're allowed to do it. So in terms of, I mentioned mining, the other half of the security model is merchanting. When you sell somebody something for Bitcoin and you validate that coin, you're providing security for the entire system. You have a say. But if that's all done publicly, large scale, you don't have the say. The people that have the ability to force you to do things have the say. So are there shortcuts to everybody who has a say having a full node? There's some things that we look at as possibilities, but non-economic nodes, just throwing up 10,000 validating nodes on Amazon, right? Completely irrelevant. Does nothing for the security of the system. They're non-economic. They can't say no to a sale. Layering, lightning, whatever, it does not change the node requirement. Every individual still needs to run their own node. Pruning does not remove the full chain validation requirement, unless you want to, again, trust a central authority for, ensuring that the data is valid. Checkpointing, same thing. SPV, we've heard a lot about that. Reduces individual power because you're delegating some part of the validation to somebody else. So the point I'm trying to make here is that Bitcoin requires people to be able to run full nodes, either as miners or as merchants, and they really can't get away with it. Can't get away with not doing it. So at Libbitcoin, we're really focused on the Bitcoin stack right now because there's still a lot of work to be done to make that very usable for development. So people can build on Bitcoin, not pull people away. So these are, Amir Taki started Libbitcoin in 2011. Libbitcoin's the first full implementation of Bitcoin after Satoshi's implementation. It's taken a while to become more mature, but it's been around for quite a while. So these are the three principles Amir laid out when we started, and if you kind of read between the lines a little bit, he's really saying what I'm talking about. Right? We need to be able to, these things need to perform well, they need to be private, and so that the system remains secure. Individuals have say, and they can do it without asking for permission, which means they have to be able to hide. So quick overview, this is the Libbitcoin stack. On the left side here, we're looking at the client side components. On the right side, the server components. There's some duplication because there's some shared components. On the right, you see the list of repositories in GitHub that implement the different pieces. The blue boxes are Libbitcoin, the gray boxes are dependencies. The dashed lines are optional dependencies that are only required in a very limited number of cases. So if you look closely, you'll see that there's actually very, very little. This is a C++ developer toolkit. Boost is a primary dependency if you C++ types, and libsec p256k1 is another. Otherwise, unless you're doing client-server stuff, there's nothing else. If you do client-server, our server, which sits on top of the node, inherits the node, uses 0MQ as a client-server protocol stack. So Bitcoin server, it builds on. We have a node, and then the Bitcoin server is a compilation of additional code on top of the node, and this is built on Bitcoin. This is itself not part of the Bitcoin protocol. It provides command line options, configuration settings as an executable, so you can actually run BS as a single file, but there's an entire library which implements all this stuff, so if you want to build your own code, take the library, build your own user interface over it. So again, 0MQ, V4 we're adding WebSockets. Haven't been a big fan of using HTTP for client-server interfaces, but it's really nice for certain local machine operations. Open up a browser, talk to the node. So we'll be adding that. So again, building on Bitcoin. The client-server interface, includes robust query services, payment subscription, and block and transaction broadcast. But pretty much, if you think about the RPC interface that you're used to, this replaces that with a very robust 0MQ-based client-server interface. That's just a screenshot of the server doing its thing. Sorry. So Bitcoin Explorer is on the other side, the client side. So we have an executable that you can use to actually run the node and server, and then on the client side, there's an executable that's basically designed as administrator tooling. So command line options to talk to the server, do cryptographic primitives, make transactions, about 80 or so different commands. Very similar to the server in its operation. It's basically a library that you can build over if you want to, but also it compiles into an executable single file, so again, very easy to deploy and maintain. No dependencies. Okay, just skip that. It's just we got a bunch of these things that describe the command operation. So the the boxes and the circles are data types, and the little oops, that's not the pointer. Slow down. These little things, HT to EC, for example, these are commands that you can execute on the command line to transition between these different data types. So the full set of commands is that's the quantity of them anyway, and what they do. Jesus. All right. So anyway, I just have a few more slides. I really wanted to, my focus here was really not to talk about all the things that is Libbitcoin. We're doing some new and interesting things on performance, and that was really the point of describing why performance is so important, because I wanted to talk about some of the new and interesting things we're doing. So these 4 topics. So Libbitcoin is very different than what you're familiar with in terms of full node implementations. There's no transaction memory pool, there's no block memory pool, there's no signature script cache, no unspent output store, and no data ever gets deleted or reordered in the store. So how do you do that? The store is a small number of memory mapped files, and the idea is as you have more RAM, the more the data tends to stay in RAM, so you're never hitting the disk when you're querying. So if you're running a high performance server that has like mine, a 256 gig of RAM, and the store is smaller than that, so the entire store can just sit there in RAM. The files are arrays and hash tables, so we get constant time lookup for every single thing that we ask for on the chain. So constant time lookup in memory. And if you're 0MQ, the client server interface that we have, can actually, you can use in-process bindings, which means if you're running an application on the same machine, you can actually run these queries in process with the server. Have your client, or run them out of process, or run them over the internet, use secure TCP communications. CurveCP is the client server secure protocol that we provide. So you can scale your client, your wallet app, or your mining app that's sitting on top of the node away from the box, or you can have it very close, depending on what your performance requirements are. So not only constant time, but extremely high performance. And I think I saw yesterday there was a description of how many wallets you could run off of Bitcoin D. Was it 200 or something like that? That to me is obscenely low. You should be able to run millions, off of one server. Obviously, if you're doing large-scale operations like that, yeah, it's more hardware, but that is the essence of scalability: more hardware, more performance, preferably in a linear fashion, right? So, interesting side note: people talk about Bitcoin scalability. Bitcoin is, in terms of transaction volume, is perfectly non-scalable. You cannot add any more hardware and make Bitcoin process more transactions. Right. But what's also interesting, and this is, when it comes into play, it's just not related to this slide at all, but it's interesting when it comes to layering, is that Bitcoin is infinitely scalable when it comes to value transfer. Right? You can transfer all of the value of Bitcoin, technically, theoretically, in one transaction. So you have 0 scalability in transaction volume and infinite scalability in value transfer, and that's really what layering is doing, is it's taking advantage of the ability to transfer large amounts of value in small amounts of data without having to increase transaction volume. So anyway, in terms of when we talk about scalability of the node, we're talking about something very different. Not scaling number of transactions, but improving the performance of your query operations, for example, by just adding more hardware, including adding more boxes. If you want to run 10 servers, it's fine. You can load balance your queries across all of them. So in achieving this, we're not making compromises. We're not making a larger store. It's actually smaller. So we had this 5 or 7 files, depending on whether you're running node or server, that implement the database. We always index all transactions. I think in Bitcoin D, that's a command line option to index transactions. I don't know why that isn't always the case, but. And we always index spent by, who spent that output, which is if you do it wrong, it's a huge amount of data. But we end up with a data store that's actually about the same size as Bitcoin D without its transaction indexing. I don't know what it is with it. And if you're familiar with Electrum X, what Electrum X does is provides an additional index over top of Bitcoin D store. So I've never run it, but basically, you let Bitcoin D sync the entire chain, and then you're going to reindex on top of that, potentially concurrently, an additional, I think it's right now probably about 35 gig of data. So our server just indexes all that data, and it ends up with a smaller size store. So in terms of time, I don't know if so we're almost there. I think it's my last slide, actually. Yeah. I want to hurry up and let everybody get to lunch. So data size is not larger. It's either the same or smaller, depending on the scenario. And query performance is, I don't think you'll find anything better. We don't have sufficient numbers to across the whole ecosystem to tell you that definitively, but I challenge anybody to find something that's better. But as far as syncing the chain, right now in version 3, it's horrible. It's really slow. That's because last year, when we were year and a half ago or so, when we were releasing V3, we were doing some prototyping on fast initial block download. We got to the point where, so we fully parallelized the database, so we can write blocks and transactions at the same time from multiple peers. So that's great, and we did some testing and we synced, this is about a year ago, so there's less data, but synced the entire Bitcoin mainnet chain in 15 minutes off of a fast network, so a bunch of Bitcoin D nodes running on the same LAN. But that's pretty good. But I didn't like it because we were relying on checkpoints to skip validation and to allow us to parallel. In other words, if you have a known block, say at 300,000-400,000 height, you can kind of grab all the blocks that are below it in parallel and wait till they're all filled in, and now you got the whole chain. But if you don't have that, how do you do it? How do you know when to start? I mean, that's a hard problem. So the solution relied on that, which I saw as a weakness, and so we decided, let's just not. There's a way to do this. It's going to take quite a while to implement. So we're going to ship V3 with a very naive initial block down or syncing process, and we'll do the work and finish it in V4. So if you use Libbitcoin node server right now, that's what you'll notice. Everything performs really great except for initial block download. It's kind of slow. Not horribly so, but it's not nearly what I would like to see. I'd like to see an order of magnitude improvement over Bitcoin D. So we've been shooting for a while. So how does that work? So yeah. So getting initial block download parallelized all the time. So it's not initial block download, it's continuous parallel block download is really my challenge, or our challenge. And the way we achieved that was by maintaining, so again, we don't have like a lot of stuff stored in RAM. Everything gets put on the disk as we validate. It stays there, and if a transaction shows up in one block and it gets reorged out, comes up in another block, comes into the mempool, it doesn't matter, it's always the same transaction, it's been validated, it's on the disk, it stays there. And we deal with things like soft forks and rule changes, but I won't go into how. So we end up building a tree of block header metadata as the node starts up. We build this tree, and we get to the point where the tree is current, we have the strongest chain, and then we organize that onto the disk. So we have a candidate array. These are blocks that are potentially going to be confirmed, and we believe it's the strongest chain. So now we start downloading, but we do it in parallel. So tree of blocks, usually it's going to be just a list, but once we find the longest branch in the tree, we commit that's being committed to disk as it becomes longest. Once it becomes current, in other words, we're now in the current time frame based on timestamp, we just start downloading in parallel from any number of peers that you've configured. We use things like standard deviation to determine which peers are fast, which peers are slow, and we kind of weed out the slower peers during this process because it doesn't matter. We don't need to give priority to smaller or slower peers because we already know the blocks we're getting. So they're not kind of voting on what's the strong chain. We're not cutting anybody out. We just want to hit the peers that are giving the fastest response. So we kind of build up speed as the data is coming in from 8 peers by default, but as many as you want. And we write all the blocks to disk concurrently. We do the minimum required level of validation to know that it's expensive data for somebody to fake. So, right? In other words, it's got proof of work associated with it. All the transactions lock in, and they all get put to the disk at the same time. So doing this now with this technique I've described, we don't have to rely on any checkpoints. We're relying on having the strongest chain with current time frame, and that can change constantly. So we're always dealing with a candidate chain and a confirmed chain. So you've got two chains basically on disk. One is the strong chain that you're constantly querying, you know it's confirmed. And the next one is, we know there's a stronger one out there, so we're going to start downloading blocks on that chain, because here comes, it may just be the next block, but it may be a very deep reorg happening, or maybe you shut off your node for a while and you bring it back up and there's 1,000 blocks behind. So we're always building this candidate chain. Once we know it's stronger, then we start downloading its blocks, and we always do that in parallel. Once we have all the blocks, we do, depending on where you are, if you're validating these blocks, there's a validation chaser that comes in behind them as they get downloaded and sequentially performs the validation in parallel, et cetera. So that allows us to reorg the candidate chain into the strong chain on a continuous basis. So anyway, the gist of it is we get to bring in blocks all at the same time, put them on the disk at the same time from any number of peers. So you can sync the chain. I think now we're looking at about, on my machine, about 2.5 hours to sync all of Bitcoin mainnet without server indexing. Server indexing should probably, I think we're looking at an additional 15 minutes, which means that all the address indexing and just the address indexing, it's the only additional index now. So pretty good. On the same machine, Bitcoin D, I think, takes about 12 hours. So not quite at order of magnitude improvement yet, but we haven't done any additional optimization over the initial implementation, so maybe we'll get there. Anyway, so the idea is simple, small node, server interface that's robust, reliable, internet capable, highly performant, that you can build applications on, wallets, mining stacks, that don't force people to rely on a centralized API service, and do it in a way that's very easy to deploy. Take this one file and put it out on your machine. Hopefully at some point, we get that to the point where we can do it mobile, we can do it embedded. You have a little tiny microchip that can validate your money. That would be ideal, right, someday. As long as we don't make blocks bigger, we'll catch up. Anyway, that's the presentation. Lunch is coming up. Any questions?
So one of the biggest pain programming on Bitcoin cores RPC, that it does not tell you who spent an output. And I always thought there is a very good reason for that. But now you said you are indexing that who spent an output. Is that right?
I'm sorry. So when you just maybe restate it, but the answer is yes, we do that. If you have an output and you want to know who spent it, that's actually a hard question. If you don't index that data, you have to scan the entire blockchain to find it, right? So we index the data as it comes in. In V3, we actually have, and this goes back to Amir's initial implementation, we have a table that's the spenders of outputs. And what you do is you take the output point, which is the hash and the index of the output in a given transaction, and you hash that, and you put it into a hash table, and then you look, when you're trying to find the spender, you go into there, and then you find, when it gets spent, we write data into that hash table so that it can be easily queried and recovered in constant time. The problem is it's about 75 gig of data, right? That's a huge amount of data when you compare it to the, I don't know what chain is now, maybe 250 or something, 150, I can't remember. It's a big amount of data, and I never liked that, but the original implementation relied on that table as part of the validation process. And what happened was in V3, I made a change to the data store a little bit, that instead of relying on the spender, which also, I think it also encodes the height, right? The height of the spend. So instead of having to rely on that, we just put a little bit of extra metadata into the transaction storage so that for every output, the spender height is encoded into the store. So that's, I don't know, megs of data, not really significant compared to the size of that 75 gig table. So that made validation faster because we didn't have to rely on that spender table, and that spender table then wasn't necessary for the node at all. So it's only provided in the server in V3 so that it can answer that one query, which is who spent this output. And it's a great thing to be able to answer, but it's expensive. So all of a sudden it dawned on me that now in V4 we don't need the table. I don't know why it wasn't obvious to me when we did V3. So in V4 we just, remember it's no longer an aspect of validation. This is just to answer somebody's query who's running a wallet or some service. So performance is still great, but it wasn't necessary to make it completely maximally performant, right? So it's still constant time, but the way it's done now is you go to the output, you look up the output, and you still have the spender height. It's already stored there. We did that, V3. And then we look at the spender height, well, we just go grab that block, and we scan every transaction in the block till we find it. It's constant time. Blocks are 1 meg, right? So it's very fast still. It's just basically searching potentially 1 meg of data in RAM. Takes almost no time, in a millisecond query or something. So yeah, we do it, and it's going to be better in V4. And what's really interesting about this is, okay, so we took this index out, and you'd think, okay, well, the process now that I'm describing is a slower process. If you're an engineer, you're thinking, okay, it's still constant time, but it's going to take more time. Probably not the case. We haven't run any numbers on this yet, but think about it. Every time we bring a block in, or transactions in, and we index that data, we're writing this table, and it's getting up to 75 gig. So it not only slows down the bringing in of new blocks, but then when we're querying that table, those pages have to be brought in and out of RAM. This is a memory map file system, right? So paging is something that we're always looking at. We always want to minimize that. So we're no longer paging all that data. We're just working in the data we were already loading previously. So it reduces the amount of data we have to write significantly, and it reduces the amount of data we have to read when we're answering that query. So I believe it'll actually come out faster when we give it a really close look. Good engineering, I guess. I don't know. It's fun. Questions, comments, smart remarks? Lunch?